Okay, let's take a look at this. So we're gonna add. Are you? I am recording. Yeah.
Could you also send me a video like go over vertical and horizontal?
How many people are wanting to see asymptote stuff? Okay, yeah, we probably could do that. Yeah.
If we have time, let's definitely go over this.
Okay. Well, we'll be able to do both for sure. We'll go through one of these and one of those, and then we'll kind of just start to look at new stuff.
Two of these, maybe?
All right, so what about this now? When we're adding or subtracting rational expressions like this, we do it just like numbers. We got to get a common denominator. Yes,
Can you do one where it's something plus something equals something?
yeah, solve an equation.
Yeah.
Okay, we can go through one of those.
Yeah.
All right. Okay, so when we're adding these up, we got to get a common denominator, right? That's our goal. And so in order to do that, we've got to factor the top and the bottom to see what are the factors of the denominators to find our least common denominator. Remember, the least common denominator is just going to be the smallest product of factors that includes all factors in each denominator, right? So if we write this in factored form, tops are already factored in this case. What can I do to the bottom of this guy?
Factor. Take it out.
So I can take out a 3, which leaves me with what?
X squared plus
8. Okay, good. And then over here, I could do what?
Nice.
Take a 6 out, okay. 6, and I'm left with
Minus
16.
16, of course.
okay, and I can go a little further with each of those.
Actually, not.
Okay, so on this one,
Negative 2 and 4.
so I can take out, or I can break this up into x plus 4, x minus 2. Okay, and then this one I can break up on the bottom into what?
X minus 8, X plus 8.
No.
4, I meant.
You did. Okay, so we got to figure out then what's going to be our least common denominator.
Those.
So let's look at the numbers first. What's the least common multiple of 3 and 6?
3.
6. Smallest thing that they both divide into, right? Okay, so then what about the other factors? What other factors do I need to include?
X plus 4, X minus 2, X plus 4.
X plus 4 accounts for, so we've taken care of the numbers, that accounts for that one and that one.
X minus 4.
X minus 4 accounts for him, and then X minus 2. Okay, there's my least common denominator. So I need to get that in both denominators, right? So then what do I have to do to the first fraction to get that common denominator? Okay, top and bottom by x minus 4, right? So we'll multiply this whole thing by x minus 4
And 2.
over x minus 4, right? Oh, and I need 2.
Yeah.
Right?
Yep.
Can we see that? Okay, what about the second one?
You have to multiply by X minus 2.
Okay, that works then. Now I've got, this is my LCD, and that's my LCD, right? Same thing on both denominators. So now all I gotta do when I add these up, I know I've got a common denominator. So I can write the whole thing over my common denominator, right? My common denominator in factored form is just that. So we get on the bottom, 6 times x plus 4 times x minus 4 times x minus 2, right? So the top, we just got to figure out what we get on top. So we're going to get, if I multiply out all this stuff, multiply divided by -5. What do I get? I'm gonna get a -10 distributed through, what's that give me? -10x plus 40. Good, okay. Now how about over here? Then I've got my plus sign. So there's everything we got from the first numerator. How about everything from the second numerator? All this stuff. If I distribute that through what am I gonna get?
Plus 14.
Okay, and in fact, let's not even put the plus sign there. Let's just subtract.
That's what I got confused about with the subtracting. Do you like distribute and then just combine like that? Or?
Yeah, we're just simplifying the top. So over here, we're gonna distribute the -7 to everything, which is gonna give us a minus 7x plus 14, right? And so if I combine like terms on the top, we're gonna get bottom, we already know, 6 times x plus 4 times x minus 4 times x minus 2 on the top. If I combine all that stuff, -10x minus 7x is minus 17x, and then 40 plus 14 is 54. Okay. Could I, there's nothing I can do in the top, is there? See, we want to try to factor the top, though. How come?
To find out some jokes.
What could happen?
Oh,
So we might be able to cancel stuff, right? If I factor the top, it's possible that we might have a common factor that I could cancel. In this case, we don't, but it's possible. You got to check. Right? You got to check and see if you do. So in this case, we do not. There's nothing I can factor on the top, and so that would be our answer, right? I know there's a couple. I need to go back and fix these. I know there's a couple where it said you can leave it in factored form. It's not doing it. Just leave those alone. I'll fix them and regrade them. Just flag them though, if you will. Flag anything that's, like if on the assignments it said you can leave it in factored form and you do it and it marks it wrong, flag it, I'll fix it. Okay. Questions? That make sense? Okay.
subtracting one?
So, no, subtracting the same thing. Same thing. There's no issue, there's no difference on that. You're just distributing a negative on the other term.
I feel like the numbers are harder on the test than that.
I don't think so.
So what do I use? One of those.
Okay, here's the hardest one I could find for a solving an equation one. All right, so I claim this is easier, right? When we're solving rational equations, we have to do some of the same stuff. We still have to factor everything, right? So we know which values of x to exclude, because anything that gives us a 0 on the bottom, we have to exclude from the domain. So the first step would just be to factor all each fraction, each rational expression, we need to factor the top and the bottom. So what's that give us? Minus right? Okay, so what values do we have to exclude from the domain?
-6, -4.
-4, -6. So those are gone. Okay. What do we do then? What's our strategy when we're solving a rational equation?
Multiply the whole thing by the
what's the thing called? We'll multiply both sides through by the least common denominator. Good, so we need to figure out, just like before, we need to figure out what is the least common denominator. What do we get?
2x plus 6, x plus 1.
Everybody agree with that?
Yeah.
Okay. So then we just want to distribute that through both sides of the equation. Multiply that through by each term. So,
That wasn't a clap.
Really always says my
How did he do that?
You asked me.
Well, you've been deceiving me the whole time. It's not just the green that was there, like a little second.
hey, I tell you what, please don't do this. Don't get off on. I don't want to have to rein you back into it. Let's just kind of keep focused on it.
Sorry, I'm sorry.
I couldn't figure it out. Very well. I need to be.
Okay, so that's what we get, right? Everybody agree?
Do you give me 2 seconds to rattle that?
It's, I'll publish these right when we're done, so you can go to the site and get it. Okay, so what cancels then?
Plus 4.
Okay, so those are gonna cancel and those are gonna cancel.
Oh,
right?
God.
So that, whoops, so that first term,
Plus
Thank
2.
that first term ends up being what?
Negative
Negative 12. Okay, what about over here? What cancels over here?
2.
Okay, so the next term we're gonna get minus the quantity x plus 4 times x plus 3. Now, one thing you guys don't do a good job of sometimes is putting things in parentheses when you need to. If I'm subtracting a product, subtracting some stuff, I'm subtracting quantity, so these have to be in parentheses, right?
Both of them?
And then over here, yeah, they do, because if one of these wasn't in parentheses, then that would imply, like if this one wasn't, it would imply only the x is being multiplied by the x plus 4, and that's not true, right? What about over here, what cancels?
X plus 4.
Okay, and so what's that leave us on the other side of the equation? Times the quantity x plus 6. So now all we have to do at this point is we're just gonna simplify everything and solve the equation, right? So we're gonna get negative 12 minus, now I gotta put parentheses here, how come?
Because just the whole thing.
I'm subtracting the whole product, so if we expand this out, what do I get? X squared
Plus 7x plus 12.
equals negative 14x minus 84, right? So then if we distribute the negative, we get negative 12 minus x squared minus 7x minus 12 equals negative 14x minus 84. Push everything over here. Actually, push everything over here, how about? So I'm going to move everything over here. I get x squared minus 7x if I add 7x. And here I've got a negative 24, I'm gonna add to this, and so I'm gonna get a minus 60, I guess. Okay? And, okay, that works.
Do we have to factor that? If
Well, you gotta solve it, so you should factor it probably if you can. Can you? Okay, what are the signs?
Negative.
So my solutions are x equals 12, or x equals -5. Now, can I be sure those, what do I have to check?
Excluded stuff.
Okay, I gotta check the excluded values. Okay, the excluded values are -4 and -6, so those are both viable. We keep both those. Right. But if one of them, if I got a solution back here that was an excluded value, it wouldn't count. I'd have to get rid of it, right? Okay. All right, so what I wanna do, how much time we got?
I don't think we're going to.
Yeah, we have time.
4.
So what I want to do today, then, tomorrow I'll do an example of a graphing one tomorrow, rational function graphing one tomorrow. Okay, but I want to talk about, just kind of introduce you to something a little bit different today, so we get through some of this stuff. Really easy stuff, really easy stuff. This next unit, it's mostly about, like today, all we're going to talk about is review stuff. We're just going to review, maybe extend what you knew before about how do we simplify, how do we convert between radicals and rational exponents, fractional exponents, back and forth, and how do we simplify radicals? That's it, no big deal. So to think about this though, I'm not gonna test you on any of this stuff I'm gonna talk about here, but I want you to know this going forward into pre-calc and calculus. I want you to kind of make this connection. So we haven't talked a lot about inverse functions this year. We did a little bit at the start of the year. Inverse functions are essentially functions that undo each other, right? So if f and g are functions, they're inverses if and only if, and that's the way we say if and only if in math, right? You might remember that from geometry. If and only if means that it's the statement can go in both directions, right? I could say that f and g are inverses if this is true, or I could reverse that and say this is true if f and g are inverses. They're connected. Both statements have to be true for this relationship to hold. So they're inverses if f of g of x is x. So if f undoes g, or I should say and, if g of f of x undoes, if g undoes f, and I get back to x if I do this composition. Right?
What's that? Is that an IFF or is that an IDF?
IFF. IFF means if and only if. And it means the same thing as if I said a two-way arrow. Okay? Each one leads to the other. Okay, so then I want you, real quick, I want you to walk me through this. Help me find the inverse of f of x equals x squared. Now, you know the recipe for finding an inverse. And what did we do? If I want to find the inverse of something, what was my recipe for that? Thank you. Really, let me forget that.
Oh, shoot. Oh.
So what do we do? Amber, what do you do?
I was gonna have to do that.
Okay. So what do I do? What's my recipe if I give you a function or a relation, even if it's not a function, I want to find the inverse of that? No. No, that's just a notational thing. It's really not a negative reciprocal. When I say that something is the inverse, like if I say inverse sine is you'll see it on a computer or on a calculator as sine to the -1, it does not mean the inverse of sine. Not at all. It means the inverse function. Totally different. Yeah.
Just square root f of x.
Okay, so we're just gonna square root, but remember, you might remember going through this train of steps to solve an inverse. First thing we do is we replace f of x with y, right? So we write this as y equals x squared. There's step one. Then we swap the x and the y, right? You remember doing this? You remember doing this in algebra 1? Really? You never did this.
Oh, yeah, I remember.
Okay, well, I'm gonna teach you this, so please pay attention to this, we're gonna do this quick. So if you wanna find an inverse, the definition of an inverse is you're going to exchange the domain and the range, that's really it. And we did that a little bit at the start of the year, we looked at ordered pairs and which ones were inverses, just a little bit. You guys remember that? In review? Okay, that's okay.
I'm starting to get a little bell ringing.
Okay, good. So we're going to exchange. Step 2 would mean we're gonna swap these, so that becomes an x and that becomes a y, right? Because that's really what it means to be an inverse. You're gonna swap the domain and the range,
I definitely remember.
and then we're just gonna solve for the new y, and that's our inverse. So how do we solve for y here? Square root. Okay, so we get the answer y equals what? No, plus or minus square root of x. Okay, so there's a problem there, right? I get two answers for this. Now, if we look at the graphs, this tells us something important.
So it's like a sideways parabola.
Yeah. So we get this parabola here, y equals x squared is really simple. It just looks like that, right?
You're gonna have to erase that out.
If I calculate the inverse, I get plus or minus the square root of x. Well, let's make the minus, let's separate these two graphs. The plus will make green, the minus will make blue. Okay, what does the square root of x look like?
Like this.
Okay, good. So it looks like this.
Like you rotated the whole parabola. And
Right.
shine that.
Okay, so minus the square root of x would just be multiplying the whole thing by -1, flips it over the x-axis. And so wouldn't I just get this is going to be the bottom
Yep.
half of that? Now, the math gods are smart. They gave us two separate answers here because the math gods are giving us back functions.
Okay,
And we
I see.
know that for a graph to be a function, it has to pass the vertical line test, right? So this sideways parabola does not pass the vertical line test, does it? Right? So the math gods broke it into two separate pieces, each of which does pass the vertical line test. If I look at just the square root of x by itself, yeah, that works, right? Or if I look at just minus the square root of x, that works, okay? Now you might see a connection here between the graph of the yellow parabola and the inverse functions that we got from it. Do you see any kind of symmetry?
It might just be
Oh, God. What kind of symmetry do you call that?
Okay, it's got reflective symmetry about the line y equals x. So here's the line y equals x. If I were to take the yellow parabola and reflect it over that line, wouldn't I get the sideways parabola? Okay, there is a little, and we're kind of getting short on time, so I'm really not going to spend a lot of time on this, but there is a shortcut you should remember. This is pretty good. I'll tell it to you now. We'll talk about it again in calculus. We'll probably talk about it next year. But there's an easier way. It's kind of difficult to reflect something over a non-vertical or horizontal line. It's a little bit tough to do that, right? To take that yellow parabola and figure out what it's going to be if I reflect it over a diagonal line. So reflecting over the line y equals x is equivalent to doing two really easy things. You could take the original graph, and first you're going to rotate it counterclockwise 90 degrees. So the yellow is going to end up going to, it's going to go to here, right? After I rotate it 90 degrees counterclockwise, and then I just reflect it over the y-axis. That always works. Okay, those two easy steps are equivalent to that one hard reflection. Okay, so rotate it 90 degrees counterclockwise, and then reflect over the y-axis, and that gets us here. Okay, so we see that kind of symmetry. But the problem is we end up with something that's a non-function, so we got to break it into separate pieces. Okay, so then is x squared, or are x squared and the square root of x inverse functions? They're not truly inverse functions, right? Because x squared is too big. X squared, y equals x squared, has two lobes. It has two sides to the parabola, and the square root of x only has one. If I want to treat them as inverse functions, I've got to kind of truncate or cut back this original function. I've got to limit the domain a little bit, right? If I were to take away this part of the parabola over here, then we'd be okay, wouldn't we? Because just this part reflects to the square root graph, right, that we know. Okay. So we got to be a little careful with that, and that's one of the problems we see when we take an even square root is an even root. Anytime we take a fourth root or a square root or a sixth root, we get kind of the same shape. We get this shape that's going to start at the origin, it's going to go up, and kind of gradually the slope decreases as we move to the right, or decreases with x. These we've got to be careful with. The original function is what we would call a many-to-one function, because there's more than one value of x. Like if I take, for example, if I go over to x equals 1, I'm going to go up to y equals 1. if I go backwards to x equals -1, I also go up to a y value of 1. So many different x values give us back a single y value. Is it a function? Sure, that's okay. Because each individual x value only gives me back one y value. But multiple different x values can give me that same y value, right? So it is a function, but because it's a many-to-one function, when I take its inverse, I get something that doesn't work. I get a one-to-many relation. In this case, I end up with, if I go over 1, I go up 1, but if I go over 1, I can also go down 1, right? So a single x value corresponds to multiple y values, which means I'm violating the vertical line test. So we got to be careful with that one, right? And the moral of the story, what really comes out of this is, can I put a negative number into a square root or any even root? I mean, I can, but I'm not going to get back a real result. I'm going to get back imaginary results. And that has to do with the fact that the original function, it never dipped below the y-axis, did it, right? Multiple x values gave me the same y value, but they were always above the x-axis. And so when I flip this thing, when I reflect it over the line y equals x, I never get back x values to the left of the y-axis, okay? It's a little bit easier to deal with x cubed. If I want to find the inverse of x cubed, I don't have that problem. I can go through the same steps. Step 1, I'll just replace f of x with y. Step 2, I'm going to swap the x and the y. And then what's my answer? Y equals what? Do I have to put a plus or minus? No. When I'm taking an odd root, I don't need the plus or minus. I just get a single answer and it's easy. How come it's so easy? Look at the graphs. So here's y equals x cubed, looks like this. That's a pretty bad graph, you get the idea, right? If I rotate that thing around the line y equals x, I just get something like this. It works, right? Both of them are functions. Okay, I don't have to worry about deleting any parts of the domains. They're both functions because the original function was one-to-one, right? No place do I have an x value. Every y value I get is only associated with a single x value, right? That wasn't the case here. Okay, and let's just think about this. This is kind of the last thing I want to leave you with. And then we're really not going to talk about this anymore. We'll talk about this in the future. But what can you see about the original yellow function here that sort of predicted in advance that its inverse was going to violate the vertical line test?
Inverse?
When I took this yellow function and I reflected it over the line y equals x to get the graph of the inverse, I had a problem. When I did that, the result violated the vertical line test. What could I have applied like another simple test to the original yellow function and said, I know it's going to be horizontal.
Yeah, that's right.
Okay, good, because it failed the horizontal line test. Now the horizontal line test isn't as big a deal because it's still, the yellow graph is still a function. But what it does predict is that its inverse is not going to be a function. So going forward with this, and this is really all I want to say about this, to kind of get you prepared to think about this in the future. We can always make a prediction. If a function passes both the horizontal and vertical line test, then you know that its inverse is also going to be a function. There's no danger of it ever violating the vertical line test, right? So odd powers of x, it's easy to take the inverse. I just get back the, a cube root in this case, and the domain of that is everything. I can plug any kind of number into a cube root, positive or negative, right? But I can't with an even root, okay? All right, so what we want to shift to now is really easy stuff. We're just going to look at doing some working with these kinds of radicals a little bit. So here's a couple properties that I'm sure you talked about. If you didn't, I'll give them to you. Anytime we write a radical, this is what we call, the n is what we call the index of the radical. And it's just telling you what kind of root are you taking. So if that's a 2, what kind of root are you taking?
Square root.
Square root. We don't write the 2, we get lazy because we use square roots so often. But a square root has an invisible 2 sitting on the radical. If it's a cube root, it's a 3. If it's a 4th root, it's a 4. If it's a 100th root, it's a 100. Just tells you what kind of root you're taking, right? If we're taking a 100th root of a number, what's that really asking? What number to the 100th power equals what I started with, right? Those are pretty hard to do, but I'll give you one easy one. 5. What's the 100th root of 1?
It's 1.
It's 1. Yeah, because 1 to the 100th equals 1, right? Okay, so another way to write this though,
Plus or minus ones.
right? If I do the cube root of 8, what is that? How come?
Because 2 cubed.
Because 2 cubed is 8. You get the idea. Okay, so we're used to seeing radicals, right? We write things as square roots and cube roots, but a disadvantage of radicals is that they're hard to do algebra with a little bit. It's easier for us a lot of times if we take a radical and we rewrite it as a fractional exponent. That's helpful because we have all these properties of exponents that we know how to use, and they still work, even if the exponent is a fraction, right? So the nth root of a we can write as a to the 1 over n. A lot of times on calculators, it's hard to find how do you find a cube root button on a calculator? It's difficult to do. They're hidden. And if you wanted to find like a 6th root, then you got to go in and you got to do a whole bunch of keystrokes to be able to find a 6th root using a radical. But it's really easy to do. If I want to take a 6th root of a number, I can very easily just take the number and raise it to the 1/6 power. That's easy to do on calculators, right? So that's one just practical advantage of that. Okay, we can go one step further. If we're taking an nth root of some number to a power, to an exponent, then I can also write that as a fractional exponent. Well, we know that the n, the index of the radical, goes on the bottom of the fraction. Where do you think the m goes? On the top. So we could write this as a to the m divided by n power. And it means either one of these. It means I'm taking the nth root of a to the m, or I could take the nth root of a all to the m power, right? Either way, I just get a to the m over n. So these are really simple. So if I want to write this as a fractional exponent, what is it? U to the 6/7. That easy. Okay. What if I want to do something like this? I want to rewrite the expression using a rational exponent. What could I do to the VWY there? Yeah, I could write those to that goes on the top, that goes on the bottom. Could I make that simpler?
Yeah, you put it to all.
I can reduce the fraction. That's the same thing as saying 5/4. So that helps us, right? That tells us that taking this product of variables to the 10th power and then taking the 8th root of that, we can do that more simply. We can just take the product of variables to the 5/4 power, right? It's a little bit easier than having to use those big radicals and those big powers. Okay, what about this one? We want to write this using, so what are we going to do? This looks like a mess, right? Okay, but I'll show you that this gets pretty easy. If you write all of these as fractional exponents, we can use our properties of exponents, and this is no big deal. So let's take, for example, what if we look at this? I know we're going to run out of time, but we'll at least start this. What if we just take that part?
X to the 1/4.
Okay, so I'm going to get x to the 2/8, which is x to the 1/4, times y to the 15/8, times, what if we do this one? X to the 5/8, all divided by, square root of y is y to what?
The 1/2.
And then all I've got to do is just, when I multiply like bases, I add exponents. So what about the x's? Then I get x to the 1/4 times x to the 5/8 is x to the 1/4 plus 5/8, right? Well, that's 2/8 plus 5/8.
Oh, that's
7/8.
why we learned how to do
Right.
that.
Okay, now I get y to the 15/8 divided by 1/2. Well, that's 15/8. When I divide like bases, I subtract, right? So 15/8 minus 4/8 is 11/8. There it is. Okay, here's our answer. Okay, what if I want to write this using a radical? Just reverse it. Well, first of all, 15/12 reduces to what?
Cube root.
Okay,
You
5/4, right?
To the fifth.
And so I could write this as the 4th root,
Yeah.
because the 4 is on the bottom, of whatever's inside the power,
So if it's a cube root, what would that one become? Quartic root?
to the 5th power, right? Okay? Make sense? Okay.
That was actually what
How about this?
Oh, God.
I mean, we just did, I'm gonna skip that one, we just did one like that.
Oh.
What about that? Okay. What do we got here? What am I gonna do? Okay, good. So I know I'm gonna get, okay, and so I gotta get a common denominator, that's gonna be 30, right? So I'm just gonna get y to the, if I multiply by 5/5, I get 25/30 minus 12/30 equals y to the 13/30. Okay, it's a lot, you might have noticed here, if you read these directions, these questions all say we're writing with rational exponents, but it says rationalized denominators. That's gonna be in the instructions for all of these questions. What does that mean? You guys have dealt with this already. No tenths in the basement, right? You can't have any radicals stuck in the denominator, right? So a radical in the denominator could look like a root of some kind, or it could look like a fractional exponent. You can't have a fractional exponent in the denominator either, okay? So we'll deal with those next time. I'm not gonna do any of that today. Last thing I wanna show you though is this, great trick, really good trick. I'm gonna show you a good way to do it. So how do you simplify something like that? Remember this, because this is very helpful. Okay, so I can deal with this, I can deal with all of the parts of this separately. So we can deal with the number part, we know how to do that. Square root of 12 is easy to simplify. But what about the x to the 5th? So the square root of 12 breaks down to what?
2 rather than 3.
So I get a 2 outside, and then I get inside a 3. Now what about the x to the square root of x to the 5th, which are a really simple way of handling this?
Pull out 3x.
Anybody have a suggestion? X to the what?
5 halves.
Okay, there you go. All you gotta do is think about this as a rational exponent. If I write the x as x to the 5 halves, think of the 5 halves as a mixed number, right? The 5 halves as a mixed number is just 2.5, isn't it? Right? That's the same thing as saying x to the 2 and 1/2 means 2 plus 1/2. Well, what is that? X to the 2 plus 1/2 is the same thing as saying x to the 2 times x to the 1/2, right? So here's the trick. When you write the variable to a fractional exponent, you're going to take the whole number part of your answer, goes out front. So out in front, we're going to get an x squared. Now, there's already a 2 sitting on that radical. That's the index, right? That's the 2 that's in the denominator. So then what's inside is going to be x to whatever the numerator is of the fraction that's left over. Get the idea? Okay, so what about this one? We can do this really quick. Next time.